Welcome everyone to the PhD-Teach-PhD workshop. We've been running this for a few years and it's great to be at least partially back in person, although welcome also to everyone online. So today's workshop is by Xiong Miao, who's one of our PhD students. She's talking on uncertainty quantification in machine learning. So I believe we're starting with half day, but potentially going to the afternoon. Is that right?
I think maybe afternoon because I only.
Okay, so yeah, probably continuing into the afternoon. So if you're online, yeah, there may be some breaks here and there. You can go and have your own lunch and so on, and hopefully everything goes smoothly. And yeah, so thanks all for attending. And I'll hand it over to Miao.
Okay. Okay. Hello, everyone. Thanks for joining this workshop. And today my topic is about uncertainty quantification for reliable machine learning. And I'm an IDS student under the supervision of Prof. Hui. And my general topic is about uncertainty quantification and trustworthiness. So this is one of my topics. And about today's tutorial, I just first want to acknowledge this course and Alexander Amini, because I generally followed his introduction course for sharing the whole story about uncertainty estimation. Because originally there has been many math staff, but I find that he is one of the most talks I have watched that can introduce this topic very clearly without introducing too much messed up. So I modified my slides to generally adopt his storyline, and I also adopted a lot of his slides due to some time limits. So you can see some watermark in some of my slides. Yeah, I'm just sorry for that. And besides that, I also adopted some other like the slides and some annotations, which generally from the paper or the talk the paper gives. So if I miss the credit, that's usually from this paper. Yeah. Yeah, and feel free to interrupt me if you have any questions, and I will have a little bit break after every section. The first section is about why uncertainty quantification. Actually, during the recent 10 years, the deep learning has gained a lot of advances in terms of the models and the performance. But actually, we can see that the real-world application deployment has been limited. And according to one survey, one of the most important reasons is that it's lack of reliable uncertainty estimates. And there are also some other reasons like sensitive to distribution shift and unable to distinguish between in-distribution and out-of-distribution samples. And we will see later that this uncertainty estimation, reliable uncertainty estimates is also the underlying factor to other domains. And uncertainty quantification helps us know when we can trust the predictions. Oh, sorry. Okay. Because, for example, like when we want to deploy our applications into the medical domain, and instead of giving a point estimate, the doctor also wants to know whether they can trust the diagnostic report generated by the intelligence algorithms. And if we can quantify the uncertainty of the diagnosis, and then the doctor can put more emphasis on these uncertain cases and save a lot of time. Because if we can model the reliable uncertainty estimates, then we can know which cases need more attention and which cases the model are more confident about. And there also another reason about why the deep learning models are limited in real-world applications, because there is distribution shift between the training data set and the tested data sets. As we can see that usually what the models we are training, like the ImageNet and like some simple data sets like CIFAR, they are actually quite clean, no occlusion and simple background, but actually when you deploy it into the real world applications, there are a lot of edge cases, like some kind of, they only have part of the animals for the dog classification, and for the driving cars, and there may be some other edge cases that I haven't seen in the training data set. So these cases are actually highly uncertain cases. And if we can capture the uncertainty, then these cases can be handled to the human to do some manual prediction, like the self-driving cars. It's predicting something, and if it's uncertain, report to the human to make some manual decision.
Do this if we want. You don't have to hold it.
Okay.
It's easier to.
Okay.
Just like it's all tied up, maybe you untie it.
Okay, thank you.
By the way, maybe have a break in like an hour, just for like bathroom and snacks, maybe with an hour before.
Okay, okay. Yeah, thank you. And it also has many other applications instead of what I have been taught, like some medical imaging or to autonomous vehicles. And it's also widely used in active learning, because actually deep learning is driven by data, but a lot of data are unlabeled. Actually, labeling data is high. The cost is quite high. So there is a problem that which samples should be labeled. If we only have a limited budget to label the data, then we can, using the uncertainty estimate, to identify those uncertain samples, and these samples should be labeled in order to mitigate some bias or some noise. And this is today's outline. First, I will discuss about the probabilistic learning, and then introduce two types of uncertainty that we are mostly consider. One is model uncertainty, one is data uncertainty, and also between this there is also distributional uncertainty, but it can be included into the two categories. And then I will discuss the 4 lines of uncertainty estimation algorithms about deterministic methods and the Bayes neural networks and the ensemble methods and the test time data augmentation. And finally, I will discuss some real world applications. Yeah. The first section is about how to estimate uncertainty estimation. Let's quickly go through the neural network framework. In this talk, we mainly focus on the supervised setting, which is also the uncertainty estimate mostly focused on. For this supervised setting, we have 2 types of inputs. One is the data and one is the target. And then we try to learn a mapping from the data to a target, which will output some kind of score. And then people usually use softmax output as softmax as an activation, because it can be integrated as a class probability. because the softmax output usually use the epsilon to make sure the score is always positive, and then it tries to use to the numerator and the denominator to attribute every output to the sum to be 1. And this has some benefit that so if we can interpret every output as a probability, like the score output in corresponding to the cut is the probability of the sample is a cut. And actually, if we go through this into more detail, we're actually modeling this the target as a categorical distribution. And we usually call this score as confidence, but this is still has a little bit discrepancy with what we call the model is confident on this sample. Yeah, this is called confidence score, but it's not perfect. I will discuss later. So, so actually, we are for the general probabilistic for the classic neural network setting, we can fit it into the probabilistic setting by considering the target class is drawn from the categorical distribution, and every class has a distribution, corresponding distribution parameters P, which you can consider the binary classification task, and then you can consider the Bernoulli distribution, where the P is a parameter. It's the same. And for the continuous, for the regression task, it also has an underlying assumption. It's like for every prediction, it's actually follow the corresponding normal distribution, and the model is actually predicting the corresponding mu and sigma. But this confidence score actually has a lot of problems. First, it suffers from overconfidence issue. Let's take the example, the simple MNIST digit classification. For this one, it's very similar to the training data set, so it has a confidence score 1. But if we just rotate it a little bit, then its confidence score drops, and it's changing to another classes. We know that this is definitely not 7. It's giving 7 a very high confidence score. So this is not what we want. And then one branch that tries to tackle the overconfidence problem is the confidence calibration. It tries to introduce interpretable uncertainty. The motivation is that it's trying to think about how we interpret the confidence score. When you see the confidence score is 7, you are seeing that this image is 70% confident it is a cat. So actually, we are attributing it to kind of accuracy. So people introduce the calibration error as confidence minus accuracy, which is the predicted probability of correctness minus the observed frequency of correctness. This is what the frequent is doing. And okay.
The accuracy of the model or of what class distribution is
Pardon, you mean what?
The observed frequency of is that how many times that particular class is occurring in your training set?
Oh no,
Or
it's
is that how accurate is your ML model in general?
no, sorry. Let's go into a little bit detail. For usually
Or is that screen?
Usually this means that it's observed frequency of the same confidence. For the mean calibration error, we are actually splitting and considering different the samples within of the same confidence score. So for example, for this confidence is 80%, then we're gathering all the samples output the same 80% confidence score, these samples, then we are computing its accuracy. This is observed frequency of correctness. But if all these samples output is 80%, but it actually has only 60% of accuracy, then it's definitely overconfident. Yeah, maybe you can consider the kind of ring prediction. Like if you see today, it's probably 70% there is a rain, but then you can gather all the years, like all the day with 70%, and you compute whether it's 70% of days that there is a rain. Okay. Oh, by the way, can I do a little bit of research out how many of you are not computer science students, or how many of you are okay? If you have any questions, feel free to interrupt. Yeah. And then the calibration's target is to make the confidence representative the true correctness likelihood. This is the definition of a perfect calibration, which is if the model outputs the confidence score P as P, and then then the probability of Y, the target equals to Y should also has the probability as P. This is a perfect calibration, and the people usually measure it by splitting the data into several bins, and for every bin they should have the quite similar confidence score, and then the accuracy should be consistent. Yeah, just as I have said before, given 100 prediction, each with confidence score 0.8, we hope 80 data points should be correctly classified. And then we find that if we follow this kind of measurement to measure the deep neural networks, we find that most deep models are overconfident. As we can see that this is the LENet, which is quite traditional. It is actually overconfidence. This line, this straight line is a perfect calibration line, which means that the confidence being is like 0. Oh, sorry, is 0.9 or 0.85, and then its corresponding accuracy is the same. And we can see that original model are quite similar, are quite fitting this line. But this is a ResNet, which you can see that it's output the corresponding confidence score as 0.9, but it actually has accuracy lower than 0.9. And for the 0.8 area, it's almost only half of the accuracy. So it's under calibrated. Oh, sorry, it's overconfident, under calibrated. And then the original paper proposed a very simple mitigation that tries to, this is called temperature scaling, which only introduces one scalar, which is the temperature T. So it modifies softmax, original softmax by every feature. It divides the temperature T. And then we can see that this performs actually quite well in the ResNet. It's like the, this is the original ResNet 110. It's overconfident, under-calibrated, and after temperature scaling, it works quite well. So usually people will add temperature scaling as a baseline.
What do they choose T?
Oh, they choose T using, this is a good question. They choose T as using a very small validation set. It's a held out data set. And then it follows the same training, try to just fix all the models, try to find the optimal T. And there are actually many other calibration methods I will only briefly introduce. For example, the histogram binning. Instead of choosing one T, it uses a validation set, but split the whole data into like 20 bins. For every bin, it try to learn a corresponding value. For example, like if it's this bin, and it has an accuracy like, let's see, 0.75, 0.75, and then every time when the test time, there is a confidence score that falls into this region. It will directly modify this value to the learned alpha, which is like 0.75. And for example, for this region, it finds that the accuracy is only 0.4. And when during the test time, for any samples with confidence score fall into this region, it will directly modify change the value into 0.4. Even though you see this method, this histogram binning seems like very simple and sounds unreliable, but it has some kind of guarantee. So that's why some kind of works are still using and study along this line. And there are also some instance-wise calibration, which the motivation is that, for example, for this being, they are totally different kind of sample, even though they output the same score like 0.8. They just have different cases. Maybe some are a little bit more certain, some are not. And then people propose that we should use information from this sample itself to output a kind of temperature score. So it actually designs some kind of different functions that try to find the T for every sample. And so every sample will go through different kind of softmax activation. And also there is another line of research that is doing Mixup. This is kind of like augmentation, that we randomly sample two samples, like two images from the training data set, and then we just combine them together to form a new images. And the label is also become softer, like these images when doing training is treated like 0.5 as cat, 0.5 as dog. And we find that this mix-up also bring kind of calibration performance. It can lead to well-calibrated. It's kind of lead to well-calibrated like this one. And also, I want to mention that in some kind of most recent models like the vision transformer and some NLP mixer, this kind of pre-trained model, actually they does not suffer from the overconfidence issue, at least not that much. And also some people attribute this to the architecture. Like if you use kind of new architecture instead of the convolutional layer, which is widely used in the computer vision before. But recently they kind of begin to using vision transformer, and we find out they do not suffer from this problem. So there is a paper that thinks it's attribute to the vision, to the architecture like the transformer one. But we also find some counter examples. So we just actually our group has kind of assumption that maybe it's not the architecture. It should be like the pre-training. Yeah, I just share this. You mean computer vision or natural language? It depends, but yeah, mostly they will mainly do experiments on the computer vision, but also will just include several experiments in other domains, but not too much. Yeah. But actually, calibrate, even though we have calibration on this kind of confidence score, we have to see the calibration confidence score is not enough. For example, for this image, we are doing the dog and the cat classification. But if this image has a dog and has a cat, what does it will output? Sometimes it will output like 50% as cat, 50% as dog. Can we see this kind of confidence score is not confident? Actually, it's not. It do captures the feature of the dog confidently and the feature of the cat confidently. But just because the data ambiguity, it outputs this kind of score. So this actually leads to a problem. Does this kind of predictive uncertainty really enough? And also for this one, if we're doing the dog and the cat classification and some user just input an image of bird, what will its output? Because the original softmax output is a closed form, so which means that the probability of cat and the probability of dog must sum to 1. So this will lead the problem that you cannot detect the out of distribution data, just like this bird. So this leads to we dive into more details about the different uncertainties. What we are talking about when we speak of uncertainty, actually there are quite different uncertainty that we care about. For example, like this kind of overlapping class, this one, even human, we cannot confidently output this is 7 or 2. This kind of ambiguity is actually data uncertainty. In literature, also called allegorical uncertainty. It's irreducible. It arises from the natural complexity of data. So, which means that even no matter how complex the model is, how many training data that you want to use, you cannot mitigate this complexity, this uncertainty. It's arises from the data. And another one we care most is the model uncertainty, which is reducible as training data sets increases because it measures the confidence of prediction. Like, let's take this example. This is one model. We only have 3 observations, and this blue line is actually the real function that is generating the data. So if we only have 3 observations, we're using a model to fit like this and output this kind of uncertainty. But if we have more data, we can fit the real distribution better. So this is model uncertainty that you didn't see much data, or so it has, for this kind of out of training distribution, they should have high model uncertainty. So to sum up, epistemic uncertainty, which is also called knowledge uncertainty or model uncertainty, they are interchangeably. They measure the unknown of the models and can be explained by unlimited data. As for the authorical uncertainty, which is also the data uncertainty, the measures what you cannot understand from the data, it can be explained by the unlimited things. And then some exercise. For this kind of images, what kind of uncertainty do we need to consider? Hi.
What is the unlimited system?
Oh. Actually, you can also see just cannot explain by unlimited data. This is, I copied from, because this is from the image, medical image processing. So it's kind of like you, which side? Just ignore this. You can directly consider it cannot explain by unlimited data. Hello. Oh.
Yeah. I missed that on the right one.
Yeah, the right one.
Yeah. Can you recall it?
Okay. So, for this one, this is a real world function that this kind of distribution are generating the data, and it doesn't change. But this time, we actually increase the training data set from 3 to 20 observations. And then we are trying to fit in the model. And if we can get a quite decent loss, then we can fit it as like this with some, So we can see that for this area, the model uncertainty actually decreased from 4 days to days. Yeah, this is what we call explained by the more and more training data.
What does it have to do with epistemic uncertainty?
Epistemic, I think it's a word like from Greek. It's kind of word which means knowledge. So it says that this kind of model uncertainty we are considering is,
there you don't have data. There's
it's limited of knowledge. So it's also called.
There you have a lot of data, so your model can't be.
So your model.
Intrinsic variance. You cannot explain away.
The intrinsic variation is we should measure it in terms of data uncertainty. And for this one, actually, this is what will some doctors will meet in the real world applications. It's kind of high data uncertainty because this kind of thing, no matter how accurate the model is, you cannot predict very accurately. So you should identify these kind of images as high data uncertainty and then handle it to the doctor.
But I don't know much about this type of images. So is it because the image is faded?
Because like there are some occlusion. Yeah.
What about the other ones?
The other one, there might be some kind of noise.
Oh,
Yeah, and because like the deep neural networks is very sensitive to some small noise. Maybe you just simply adding some kind of base noise, it will change. Yeah. And for this one, if we are training, like gathering some images, like some dog images like this, and then you are input some images like this to the model, and this should be identified as high model uncertainty because it has some kind of domain shift. And then the question comes, since we are considering different uncertainties now, how to model different types of uncertainty. For the data uncertainty, it actually can be directly estimated by the deterministic model, which means that for the original classic neural networks, it's output some kind of confidence score. Imagine this confidence score is actually outputting the data uncertainty. Which means that if the model is uncertain, it will try to input a little bit low confidence score to that predicted class. And you can measure it by some entropy or variance. This is also kind of very common metrics that used to measure the confidence.
But in this case, isn't like the question that you ask the model to train to classify whether there's a cat or a dog? Is that the objective of the model? And if you present the model with a picture that has a cat and a dog,
yeah,
it actually maybe outputs the correct answer. No?
you mean output this one? Oh, sorry, what?
Yeah, like what's the objective of the model?
For the deterministic model, it's just like for classification, the cross-entropy loss, for regression, the
But in
and
this case, you cannot even yet it's a human. I cannot classify this as cat or dog.
yeah. But
So
you
why would you expect the model to be able to?
oh, we didn't expect a model to classify very well.
Yeah.
We just want the model to know to flag that this is a high uncertain images. His prediction is highly uncertain. So by outputting some kind of score like this and a high entropy or high variance, it has high, yeah. And for the model uncertainty, it cannot be estimated directly by classic deterministic model. This is because for the classic neural networks, where modeling the input and output as random variables, and for the model, once the training is finished, we only have a fixed set of weights. And so in this case, no matter how many times you run or how this model doesn't change, which means that this model has no kind of random kind of distribution that we can model. So the model cannot output some kind of model uncertainty to share that whether he knows or not knows. So one of the solutions is to change the modeling. Instead of modeling the weights as deterministic, we actually model it as follow some kind of random, some kind of distribution. So this is kind of Bayesian neural network are doing. They are treating the model parameters as random variables. So if they are modeled as a random variable, variables can have some kind of distribution, then we can kind of learn a posterior over the weights. Oh, sorry, there is a okay. just to answer the question, the difference between the data uncertainty and the data diversity, I think I'm not quite sure what's the formal definition of data diversity, but I think data diversity can be included into the data uncertainty maybe. But actually the two terms, their meaning are a little bit different. Like the data uncertainty, you are saying that whether the data is actually, for example, it's like a dog, whether it's a dog, or the diversity. It's more like the training data set has different kind of data. I'm not quite sure.
Yeah.
In terms of the data diversity, there's also one case is like if the training data set is not very diverse, and then when the test distribution is a little bit diverse, then it will result to high model uncertainty. I'm not sure whether I answer your question.
I mean, when you look at the training data,
okay, let's come back to the Bayesian neural network. So, it's very classic, the Bayesian modeling, how like we assume this kind of data, this kind of weights, they follow a distribution, and we have a prior about this distribution. Let's see if the weights follows a Gaussian distribution, and then we try to learn what if this model, they have seen the data, then the posterior distribution, because we do not know what the weight. Okay.
How do you choose which dial for?
It's really it's kind of the domain knowledge. It's expert. Because it's human defined. It's defined before you begin to model this. Yeah. Yeah, and then we just try to applying the Bayesian rules here. This is the prior about model. For example, like the Gaussian distribution. And then this is likelihood of given these weights and given the data, what's the probability of the target. And then we're trying to apply the Bayes rule to learn the posterior network. But actually, this kind of is intractable, because computing this one is very difficult. It requires some integral. So this will lead to different branches of how to approximate this one. Okay. Okay. Then one of the naturalist way is to do sampling. This is actually the earlier Bayesian neural networks are doing, I think. It's by sampling the different weights. For example, sample T different models and try to approximate the posterior. And I will cover two of the ensemble methods, which is usually using the sampling. One is Monte Carlo dropout, one is deep ensemble. Monte Carlo dropout is still following the Bayesian neural networks framework, but deep ensemble is viewed as non-Bayesian ensemble. And these two are, I think, the most highly cited paper in this area. And this one is doing test time ensemble, and this time is doing training time ensemble. I will discuss later. First, let's talk about the basic neural networks, about the Monte Carlo dropout. The general framework is like, we know we have a prior distribution about the other ways. So every time we just sample different models, and then we try to learn different target, So we learn different model, and for every sample, we can have different kind of outputs. So a natural way is to do kind of mean for the prediction, mean expectation, and to measure the variance for the model uncertainty. This is just kind of framework, and I will discuss later how to go into the details. So the first one is about the method called Monte Carlo dropout. We can actually, from the name, you can tell it's kind of using the dropout as a Bayesian approximation. The idea is very simple. Instead of considering the weights, they are actually introducing. They are actually assigning the randomness into a dropout. Just follow the classic convolutional neural networks training. Because the classic neural network, they will use dropouts to do regularization to mitigate the overfitting. And it actually provides a very perfect distribution, because the dropout we set up its Bernoulli distribution. So every time we will sample a digit. It can be 0 or can be 1, and the probability of being 1 is modeled by this parameter p. So yeah, so the dropout is a form of stochastic sampling, and each dropout is a different sample. So every time each dropout, it actually samples a different neural network. For example, this is the original fully connected one, and every time we do some dropout, then it can be seen as a sample from the posterior distribution.
What's S?
Oh, S is like it's kind of like for the model. You input X and then you can compute the mean, and this is kind of data uncertainty. So it's about the X variance. For example, if you are doing like the regression task, then for every task you let's only consider this model as the deterministic model. Then it can learn some models mean prediction about regression, and it also can, because we assume this data follows a Gaussian distribution, so it can have kind of the sigma. Yeah. This is so the whole method of this is like we're only doing we're doing training, we use MC dropout, and doing testing, we just randomly sampled so for example T samples of that using the different dropouts, and then we compute compute the variance to approximate the posterior distribution. And actually, this paper, they have quite elegant formalization to attribute the MC dropout to the original, I think to the Gaussian process, and using the variational inference. I didn't include the details here. If you are interested, you can discuss with me later, or I can see whether my backup slides are enough to discuss this clearly. So I just escape here. And then about the deep ensemble model. This deep ensemble model is more natural. For example, if you 4 points, and then you do not know you want to know the model uncertainty. It's then how about you just learn different models, like learn T models by using different data or different initialization. Just independently train different models and to measure its kind of variance as model uncertainty. So the idea is very simple, and the different follow-up work, just a lot of them focusing on different kind of initialization, or what kind of model do we need to compose the ensemble. It's I think the idea is very like original random forest or some, just the very traditional ensemble.
Sorry, what's the difference between the A and C?
A and C. Oh, A is you can see that A is one of these model. Yeah, because A is directly approximates the variance, and this one we'll cover later. Because actually, confidence score can be seen as one of these, but the confidence score doesn't. It's not able to measure different kind of model uncertainty, data uncertainty, or distribution uncertainty. Then we'll discuss here. Also, actually, simply using confidence score cannot do this. But if you want to do some metrics in terms of confidence score, it's able to capture some kind of distributional uncertainty. Like one paper who are doing out of distribution detection. Like for example, out of distribution detection is like you have some training data set, and then the test set, for example, the dog and the cat classification. You input a kind of bird, and its assumption is like, for example, for this one, if you output a normal or uniform distribution, like for every class, uniform discrete distribution, it assumes this is out of distribution data. So, but actually we know this is not out of distribution. The out of distribution data we care is it has, So for that one, the confidence score is not enough. Yeah, and then for the deep ensemble, it's very simple. Like we independently train different models, and then we measure its kind of expectations through this mean and this empirical variance. Okay, this one. Okay.
Because here the model is also involved, how can you tell that it's data uncertain? I'm not very sure, because some data here, and then you pass through a model.
Yeah.
And it gives you 50-50. How can you say that it's just uncertainty inside the data, and not because of the model training a certain way that gives you?
Yeah, it's a good question. Let me think about. Usually we Actually, it depends on the interpretation. Usually, we explain that there's the model is deterministic, and the output is actually measured the I think generally we will call the confidence score as a predictive uncertainty. The predictive uncertainty is kind of like a total uncertainty. It has a data uncertainty and it also has a model uncertainty. But yeah.
So it's very hard to decouple these two.
Yeah. For the confidence score, it's very hard to decouple these two. Yeah, and what we're talking about, if we are speaking about the confidence score, we're kind of talking about the general predictive uncertainty. Yeah. As you can see, this kind of Bayesian neural network or this kind of ensemble-based method, they're actually very computational expensive. They require training the model, for example, at T times or sample the model T times. It's not the computational time is very slow, and sometimes if we train T models, we have to store T copies of the model, and sometimes it's very sensitive to choice of prior, and it's often overconfident. So that also leads to another branch of method, which is the deterministic model. The deterministic model is one branch of deterministic model is evidential deep learning. I will cover here because actually the acknowledgement I made is actually the author that designed the evidential network for regression, and I just adopted a lot of his slides discussing about this. Let's first recap of what are these kind of ensemble method, the sampling approaches are doing when they to approximate the uncertainty. Just like the Bayesian neural network, let's just have a look. For example, for this regression, for this image, it tries to predict the angle the wheel need to rotate, and this model will output the mu and the sigma. The mu and the sigma is the data uncertainty. The mu is the mean prediction, and then it tries to approximate posterior. It will do the ensemble. It samples different models from the distribution, and then if you visualize this kind of output, the mu and the sigma in these 2D pilots, we can see that one mod for one input, different model will output different mu and the sigma. It's kind of like in the it's kind of like where approximate the original distribution. So it's kind of there is an original distribution, but we do not know. Then we're using the sampling to do this, and then we approximate by using this kind of sampled points. So there is a question. Is able instead of drawing samples from the distribution and approximate it, can we just directly learn this distribution? Because Because if we have some kind of assumption about this distribution, we can just simply learn its corresponding parameters. And if in this way, I will discuss the distribution later. I just say if we can learn the distribution's parameter, then we can kind of visualize this. For example, for this point, maybe for this sample, it has this kind of small mu, small spread in mu and a small spread in sigma. So it actually has a low data uncertainty and also low model uncertainty, which means our model is quite confident on this prediction. And for this one, we can see that it has small spread on the mu, but a large spread on the sigma, which means that the model is highly unconfident on this sample data uncertainty. So it's high allegorical uncertainty, data uncertainty. But for this one, it actually has a large spread in the mu, the x-axis. So which means that different models are predicting different value of this distribution. It has a large model uncertainty. So if we can model this kind of distribution, then we can directly compute the metrics in terms of this distribution. For example, we know this, then we can compute the variance of this distribution or the uncertainty. Yeah, that's what we are going to discuss about. Yeah.
So like just so you understand, like you run this ensemble with many different observations.
Yeah.
And then for each observation, you get mu and a sigma.
Yeah.
And then you plot the distribution for your training set.
Yeah. Actually, because let's recall what we are doing for the base neural network.
Yeah.
Actually, we are measuring the data uncertainty as or the model uncertainty as a variance of mu.
Yeah.
And so which means that actually we're just kind of measuring this distribution's variance. So how about we directly learn this instead of sampling? This is an assumption.
Like go back to the comparisons ABCD.
You mean this one or
No,
the model one?
So would you say the different? So with B, you are like doing multi-color samples on the weights. So, so you can generate as many or as little realizations of the network, just so you can sample the mean and the variance.
Yeah.
Now, for the ensemble method, the number of models is predetermined. So you determine before you evaluate the model how many ensembles you're gonna have.
Actually, for these two,
Yeah.
the number of ensembles is defined by you.
Yeah.
It's by the user.
By the user.
Yeah. So actually, the calculation formula is quite the same. Yeah. The difference is just how the weights, the models come from.
But in the case of B, let's say you wanna do 10, you wanna sample 10 times.
Yeah.
You predetermine how many, but you don't know for each of the samples which weights are gonna be realized, right?
Yeah.
But then for C, would you say that each of let's say you wanna have 10 models, would you say that each of the weights are?
It's also it's not pretty.
Like not predetermined, like after you train and then you.
Yeah, then you
fixed.
yeah, it's all fixed. Yeah.
But then for the Bayesian.
The Bayesian you
never
cannot.
know what you're gonna sample, right?
Yeah.
Okay.
Yeah. In
So
terms of this way, this is
So
Bayesian
it's very hard to evaluate, because for each evaluation you need to do the sample, then you need to evaluate the network. So whereas for C, you already pre-compute all the weights, so you already have like the predefined number of weights that you which you would like to.
Yeah. But actually, during the test time, you can also fix. For example, it depends what it's also okay. You sample 10 models, and for every input you use this same. Because this model is independent to the input, so you can for all the model you can using the same sampling. Yeah. Okay, so I just want to mention that we already this kind of sample, this point is already follows the distribution. Let's consider the classification task. The output of the target is already follows the categorical distribution. But actually, we are learning a model that can sample a categorical distribution. So it's a higher order distribution. Let's consider the regression task first. For example, the target Y follows the Gaussian distribution, and the mu and the sigma is this Gaussian distribution parameters. And as I have showed the pilot, we actually sample different mu and the sigma and try to approximate the distribution of mu and the sigma. So how about we just assume the mu also follows a normal distribution, and the sigma follows the inverse gamma distribution. Actually, there are a lot of choice for choosing this. This is a prior, you can define it, but people will usually choose the conjugate prior. I will discuss later why. And then we can see that the mu and the sigma are following the normal inverse gamma distribution. And let's look at this kind of higher order distribution, which is also called the evidential distribution in evidential deep learning. We can see this. Okay, these are just a different kind of. Actually, the mu and the sigma are following a normal inverse gamma distribution, which is parameterized by these four parameters: the gamma, lambda, alpha, and beta. These four, and then we can sample it. Sample from this normal inverse gamma distribution, and they have different kind of points in this distribution. If we sample this one, then we take a look at this. So it's actually we are sampling the okay. Let's define these parameters. The distribution is already defined as like this. So we sample one. Okay. This is one. One normal inverse gamma distribution, and different points in this distribution corresponding to different Gaussian distribution. For example, for this one, it's quite flat Gaussian. For the inside, it's quite a sharp Gaussian. So for this sharp Gaussian, it usually has a low model uncertainty. Oh no data uncertainty. And for the classification task, since we already discussed about the target class follows the categorical distribution, then we just choose and the categorical distribution follows P, the parameterized by P, and then we try to assume that P is sample from the Dirichlet distribution. And then we can see this is a 3-class classification, and this is the Dirichlet distribution. So K equals to 3, and we set the alpha to be 555. So which it has this kind of concentrated mass probability here. For every corner, it's kind of a categorical distribution that we call perfect prediction for class 1. Because for this point, if we sample, then its corresponding sample is like this. This categorical distribution means that for any sample, it has a probability 1 corresponding to class 0 and 0 to other classes. And for this corner, the sampled points is a kind of categorical distribution with the second line is equal to 1. So it means the probability of class 1 is 1. And this is corresponding to the class 2. And for every point, for example, like this, which means that it has 0.5 probability to class 1 or class 0 and 0.5 probability to class 1 and 0 probability to class 2. This is how the Dirichlet distribution look like. And for if we set the alpha like this, alpha 1, 2, 3, they equal to each other, then usually the highest density will fall into the center. And if we set, for example, the first alpha to be very high and other to be very low, then usually this highest uncertainty, highest density area, this will fall into this part. Okay, let's discuss why and how we choose this kind of posterior this distribution about the high order distribution. Actually, it's kind of conjugate priors in let's look at an example which is very simple, like the binary classification, the Bernoulli distribution. I think in high school we have learned that the Bernoulli distribution is like the probability of class 1 is P if you set the Bernoulli distribution's probability to the parameter to be P, like 0.7. And then if there is some kind of real cases, like for example, if you just have a coin which the front side is up, the probabilities you range it from 0 to 0.5 to 1, and you can see that actually the corresponding P follows a kind of beta distribution, and the Dirichlet distribution is the extension of beta distribution. So that's I think the earlier knowledge about the conjugate prior of mine, and it's actually about the definition of conjugate prior is that if you set the this is the likelihood it follows the distribution, and this is prior. If you set the prior as the likelihood's conjugate distribution, then its corresponding posterior distribution will be the same distribution family. For example, if we can set the prior to be a Dirichlet, we can define it. And then the posterior will also be a Dirichlet if this likelihood follows a categorical distribution. So that makes, because it is because this denominator can be analytically calculated. So it's kind of for computational simplicity. But it's also very useful. And let's consider for how the model training, the evidential network. Since we already said that this is a deterministic model, so actually it follows the same deterministic models framework where it put the data into the neural network and then it outputs some kind of score. But for this time, it does not output the confidence. It tries to output the parameters for higher order distribution. For example, for the Dirichlet, it tries to output the vector of alpha, which means every class corresponding alpha. And for the regression, if we assume it is normal inverse gamma distribution, then we output these 4 parameters. And during training time, there are different objectives. I will discuss two of them. For this one, I think it's adopted by evidential network for regression. It has 2 objectives. This one is the main objective, which is try to minimize. For this is the standard MSE loss, which tries to minimize the predictions, the distance to the original target. And then we also multiply it with evidence, which is probability of this. So the idea is that if the model makes the wrong prediction, then this wrong prediction should have low density. For example, in this, if any sample falls into this area, it's actually the wrong categorical distribution. For example, if the data falls into class 0, and then the categorical distribution falls like there, the error is very large, then we try to minimize its probability here. So if it makes a quite correct prediction, the output categorical distribution is very similar to the target, which is this corner. Then we try to increase its density. So therefore, we're actually pushing the posterior network to like this area. So for this sample, it's class 1. Then it can learn a corresponding posterior Dirichlet distribution with most probability mass lying in this area.
The labels for this one, we use the outputs which are
the classification. Yeah.
And use those on the other model to get what the.
Sorry, I have missed a little part about this. For this one, actually the model is output the classification alpha. And for the alpha, we actually have a Dirichlet distribution like this, so we can compute the mean of this Dirichlet distribution. That mean means
alpha.
Alpha actually is the Dirichlet distribution's parameter, but this is a distribution. It has a mean and a variance. And the mean, for example, is like this point. It corresponds to a categorical distribution. Yeah. And then we just treat the mean as a prediction.
Just to the classification alpha has no relation with the alpha in the four terms for the regression, right?
Well, you mean this one,
Yeah.
this one? Oh, it's not. Yeah, it's irrelevant.
So, how do you use those? If it's a regression case, then
Yeah, for regression, if output space, these distributions parameters. For classification of outputs alpha, and for this regression, we can see that if we learn this, we can form this distribution. Yeah, and since we have this distribution, we can compute the mean of this distribution, which we can view it as a prediction of this mu.
okay, but how do we know what the true label is or the
The true label, because it's a supervised setting, we already know the data's corresponding label.
yeah, but here the output is not the label, right?
Yeah. The output is not a label, but we can quickly compute the label just by computing the distribution's mean. Let's take this. For example, the neural network outputs alpha, a vector of alpha, and then we get this distribution. And we know the highest density point is here, it's the mean. And then we just treat the mean as the prediction of the categorical distribution because it's a the mostly sample point. If we do sampling, it will most likely to fall in this area. Yeah. So do you have okay?
So then you sample from the mean. If you go back there, then you sample y using the mean that you. So let's say you find alpha.
Yeah, we find alpha.
Then you take the mean of the Dirichlet distribution. Let's say it's called b hat.
Yeah.
And then you use b hat to sample y.
No. B hat is a prediction of y. We think. Yeah.
Oh, is a prediction, but b hat is a probability, right?
B hat is not a probability. Because like for example, for the Gaussian distribution, the mean is actually a point in the Gaussian distribution.
But in this case, the
so
mean of the Dirichlet is
so it's a p. Yeah.
So categorical of p.
Yeah. Then you can. Sorry. I didn't say this. So it samples a probability vector.
Yeah.
But this probability vector is just as like the original output of the neural network.
Yeah.
So you can also apply to choose the maximum one. Its corresponding index as a class label.
So like it's like you apply the softmax, right? Like when you started our workshop.
Yeah. It's kind of like applying the softmax, but there we don't need to apply the softmax. It's already output a probability vector.
So let's say now you have p hat, then you take the highest p.
As a label. Yeah. Actually, here you don't really need to choosing the label. You can the y you can choose it as a probability vector, and because the output the prediction. For the y, it is one hot embedding. Okay, yeah. And for the regression, they also add another term as a regularization, which is to make the input to be the highest. It's kind of maximum likelihood. Actually, this one, if we take the integral, it should be py given m. this is given the distribution, the likelihood of seeing the data. So we'll maximize this as a regularization. Hmm? M is a model's parameter. Given M. Yeah, you can see. Actually, it should be this one. It's this. Yeah, because the theta is the sample point from the higher order distribution. And yeah, and actually there are also some other line work that are at the same time, and they both derive the same kind of evidential deep learning way, which learn the deterministic model. The difference is that they have different kind of objective function to achieve it. And this is another line, the prior network. This is a work from Oxford, I think. Yeah, and the point of here is that it tries to explicitly handle the out of distribution data. So it has a, it's kind of, the out of distribution data is like you're training this kind of dog or cars or this kind of data set. And then the out of distribution data here will only mean that those samples that are semantically different from this one. And the assumption is that for the dirichlet, if it learns a dirichlet which is highly concentrated on one point, it's confident prediction. And if it's concentrated on center, it has high data uncertainty. This shares, and if the point is the whole probability mass are flat on the whole area, we view this kind of the data that learns this kind of posterior distribution should be out of distribution data. Yeah, because even yeah. So it achieves this by using the KL divergence. Whether you know KL divergence, have you? You can simply consider it as measuring the two distributions, the distance or difference. So if you are minimizing, okay. This prior network has two items. We only consider first items here. It's kind of for this model, for this sample, we predefine a Dirichlet distribution, and then the model will learn a posterior distribution. It tries to. There are two Dirichlet distributions. It tries to minimize the distance between these two distributions. Just for example, we define the model, and then we learn the distribution. We're trying to push this distribution to match another one. And for the in-distribution data, we try to define the Dirichlet distribution like this one, which is it's kind of like one-hot encoding, because here, let's see. Actually, it's defined instead of defining alpha. Alpha is a vector. Every item, every element corresponding to one point in one class. And instead of modeling every alpha, it's trying to specify the mu. So this time it's also the probability vector. Because all the mu are summed to one, and it's also the mean prediction corresponding to one class. Because the Dirichlet distributions, one probability is that its mean value is for one class, it means the alpha c divide the sum of all alphas. So it's divided this kind of one-hot encoding. Because the KL divergence cannot handle KL divergence cannot handle the corner case, so it adds a little bit epsilon to other classes. Let's ignore the details first. The whole idea is that it's just tries to define a very sharp posterior utilizing the labels. And for the out of distribution data, because if you simply using this one, they find that it's actually doesn't handle the out of distribution data very well, and they design this model. One of the important reasons is to detect those out of distribution data. So they just include the out of distribution part, try to define out of distribution for the out of distribution data. They try to specify its corresponding Dirichlet as setting all alpha c equal to 1. This is the most flat distribution. Every point in this whole area has the same density. So it tries to push all the auto distribution data to this kind of flat distribution, and then they use some kind of entropy, distributional entropy, differential entropy to capture this data. If it's a flat distribution, posterior distribution. Okay.
So because they observe that when the data is out of distribution, posterior is flat, or is it that they want the posterior?
They want the posterior to be flat. Yeah. But yeah, because actually you can see in this assumption, all the auto distribution data are going to the same point, the same kind of point. You can think it's kind of like in a higher order distribution. All the distribution in a higher order distribution, all the OD data are going to one point. It's a very strong regularization. And if you do not explicitly modeling this, it will be a little bit hard for model to do this. So that's why they incorporate some auto distribution data here. And this kind of auto distribution data usually generated by some generative model or using auto distribution data sets. For example, if you are training kind of a dog-cat classification, then you will use a bird data set or some other clothes or whatever you can find just to do as the auto distribution data. But actually, these two are not not a good solution. Oh, sorry, another good solution. Because like if you're using a generative model, generative model is actually more computational than the neural networks, and you have to train the in-distribution data to generate those. So it's computational expensive. And for auto distribution data set, it's very biased if you can, for example, like you consider the dog cat and you use bird or you use clothes, it may lead to different model, and the you need to choose the reasonable or the out of distribution data performs better. So it's kind of like you incorporating some unreasonable bias into the model. And then there are some of the follow-up work that are trying to avoid introducing the out of distribution data. This is one of the follow-up work called posterior neural network, which use introduce a normalizing flow. For every class, it tries to, for example, there are two classes, binary classification. It will learn a normalizing flow for every class. For this class, it's a normalizing flow. For this, is another normalizing flow. And then for every data point, you can get a density in this normalizing flow. You can also get a density. For this point, you can give a high density point in its own classes corresponding normalizing flow, and the low density in other classes corresponding normalizing flow. So you use this density to compute the beta, to compute the parameter, and then you just you can use this beta to replace the alpha. Let's say you have a prior. Let's recall that the Dirichlet distribution. For every, we need to learn every class's corresponding alpha, and in this case, it replaces the alpha to be it just split the alpha into two parts. One is the beta prior, one is the learned beta. The beta prior is usually one. It starts from a flat distribution, and then it learns the beta. The beta is like we have some n, which is kind of a predefined budget. So for every class, it has the same n, and then we multiply its corresponding density. So if it's a zero class, it has a high density on the zero class corresponding normalizing flow. It learns the distribution, and then it has a high likelihood in zero class, so it should has a higher beta. And for it's quite far away from another distribution, so it has a low density in other distribution. So so finally the beta, well, the vector of beta, the corresponding class has the highest value. It achieves the same effect. And for those out of distribution beta, it's far away from all of this distribution, and it has low density in every class, and then it should lead to a quite flat distribution. This is kind of the same idea with prior network. It only instead of let the model to predict the alpha, it tries to compute the alpha by learning another normalizing flow. And then the kind of loss objective is also the same as this one, only have this part. The reason
It's just you guys too. So you start with the three normal distributions at the top.
yeah.
Then use normalizing flow to remap them to the latent space.
Yeah.
Then you do that by training, like when you're training. Then you take the data and you compute a very light simulation space.
Yeah.
Then you can compute the probability.
Yeah.
And then you can arrive
yeah, you can derive the Dirichlet parameters.
Mhm.
And the previous work is ask the neural network to directly predict the parameters, and they achieve the same.
So there's a latent space of the Dirichlet from this probability is Dirichlet probability.
No. This one is normalizing flows probability. Normalizing flow is a generative model. It maps mapping from the high dimensional Gaussian to the data distribution. So you can compute the exact likelihood of this data point. So using this normalizing flow. Yeah.
But how do you choose the Z like the
Z.
I know how do you choose is that like are you gonna compute the Z1 there like not maybe the Z2?
Okay. Because you have three normalizing flow.
Yeah.
Then for every normalizing flow, you can compute the corresponding Z.
Can you pick the highest one?
No. I compute all of them.
Yeah.
And I compute because actually the alpha beta is this beta I is a vector.
No, but I mean like when you put the data in the latent space,
Yeah.
like how do you know you're gonna pick the grain distribution? Like here I can see the grain distribution.
Because this grain, for example, this grain distribution is learned by using the zero class.
Okay.
So if you input zero class, you map into this area.
All right.
If you input the sex, the map into this area. If you input this, maybe a map to this area.
Yeah.
So the Z is the data. The data's latent, and we just learn latent.
So the green distribution corresponds to the first class, and
The second one corresponded to.
So the second class.
Yeah.
The blue one corresponds
To the third class. Yeah. Here we only show three, but yeah.
Because like if I map like first class and the third, then the blue distribution would also get to the bottom. So like. So that's why I confused. Like this is during training.
Sorry, I didn't quite understand your question, but I try to explain more about. Actually, this normalizing flow is learned on the this Z is generated by the model. So the model learns the latent feature, which is a low dimensional data, and then we learn the normalizing flow.
So first step you learn the model.
Yeah, learn
The second step is to learn the normalizing flow.
Yeah.
Okay.
Yeah.
Then so you're saying put the input into the model, then you give you a prediction. Based on that prediction, you choose the distribution you're gonna use to compute the distribution.
Well, I didn't say the more one. Let's go through first. For this sample, we use the neural network to compute the latent feature Z.
Yeah.
And for this Z1, we will inference its corresponding likelihood in every normalizing flow.
Okay.
And then we derive the three density corresponding to every class.
Yeah.
And then we have a budget N. Then we use the same N to multiply every density. And then you derive the beta.
Yeah, but in the end, it seems like, how do you know you picked the green one for the first one?
How
Like what? Like it could compute that P using the blue distribution.
Yeah. Because I will use. I have this Z1. I will compute its density in this green, this red, this blue.
Okay.
I will give three. These three densities. So they actually have three three densities, and we all compute the budget to derive three beta.
Oh, okay.
There's every beta corresponding to different classes.
Yeah, okay.
Yeah. Then we get a vector of Dirichlet distributions parameters.
Okay.
And then
Okay, because the diagram seems like that for each one you only pick one.
oh no, it's actually compute the three one
So
for
for
this. Yeah.
So in total it completes 9 in this case.
Yeah, compute 9. Yeah. Do you have any questions?
So also have to think like after what point is it now something like a flat posterior? Is it how we try to find out whether the input is out of distribution
Oh,
is so whether the posterior is a flat.
yeah.
So we would also have to pick like after what point is the posterior now flat.
Oh no. For this posterior network, they don't need to force to be flat. The assumption is that you're learning a normalizing flow, and you only have high density area in those in distribution. For example, this is the whole area for like the latent is 20 dimension. Then for this class 1, it only has high density in this small area, because all the class 1's latent are into this area. And for the class 2 or class 6, you learn kind of high density area in this area. This because most of the sample sets fall into this area. Yeah. So it's assumption that the normalizing flow only concentrates on this covers the high this area. Those data usually occur to. So, which means that in those different when in those areas where the data doesn't cover, it should have low density. So for this area, the data doesn't appear in this area. It has low density. Then the density should be very low, which means that the beta is all the whole vector, all the beta should be very close to 0, and then plus the 1 is all close to 1. So it's quite flat. It derives a flat distribution.
And then the ANC is different for each class.
NC.
So like.
Oh no. NC is
like when you need NC, is like a constant.
I think it's a constant. It's a constant. It's a budget you.
But then the Dirichlet distribution is multiply all the parameters by a constant, and it's the same distribution.
No.
Like if it's 1, 1, 1, and then if it's 2, 2, 2, it's the same or not?
No. 1, 1, 1 and 2, 2, 2 is not the same. Yeah.
So what is the blue region then?
The blue region is corresponding to another class, whose data will usually fall into this region, and then we learn a corresponding normalizing flow in this region.
Yeah, now I get it. So each point of the triangle there, 6, 4, 0 corresponds to an evaluation for each of the distributions.
Yeah.
And that's how you get the Dirichlet.
Yeah. Do you have any questions? Okay.
And then, so now I understand the diagram. So like, let's just go back to what was your initial objective? So now you have the Dirichlet parameters. So you're gonna have for each input you have a different Dirichlet distribution, right?
Yeah. For each input, we have a predefined Dirichlet, because we have its class its target label.
Yeah.
So we can predefine a Dirichlet distribution. And then we also learn the Dirichlet distribution.
Yeah.
We try to match them. Yeah. Yeah, and that KL divergence provides the supervision signal for back propagation.
Can you see the formula for
Yeah, it's actually this one, because the prior networks, the most important motivation is to try to remove the introduction of the out of distribution data. So it only have this one.
So you only want to work with the ensemble method.
Yeah. Then actually, I need to point out that the work success is actually relies on the reliability of normalizing flow. Actually, the normalizing flow has also suffers from some problem. Like it's also, if the dimension is larger than 50, I think at least 50, the high density area is actually equal to the high, it's not equal to the high probability mass area. You can, this is called Gaussian, the bubble soap, the Gaussian surface. I forgot the name. But you can imagine if the dimension is larger than 50, the Gaussian distribution is not what you imagine in like 2 or 3 dimensions. Of course, we can know that the highest density point is still in the center, because you can know that right, that kind of is in the center of the mu. But actually, the high probability area, most of its probability is fall into it's kind of a sphere. So actually, it's more like a bubble. All the probability mass is on the sphere, not the center. But the center has the highest density. So if you rely on the highest density, then it has some problem, like some out of distribution data or some totally black or white images or something will fall into this high density area. But it's actually not the training data set. Actually, it's in the latent space. You can choose whether it's high dimension or low dimension. Yeah, but I forgot the detail. But I remember when I was reading this paper, I think my memory is that even though they claim they try to reduce the dimension a little bit, but the dimension is not so low. For example, like the sigma 10, maybe it's 200 or so. It's not, because the origin, yeah, for data, the original sigma 10 is like 3,000 and it's more than 3,000 dimensions, because 3 multiplies 32 multiplies 32. Then it reduced the dimension like to 200. But it's 200, it still suffers from this kind of bubble effect. And then let's come to the last one. This actually is the most simple one I see. It's test time data augmentation. The idea is very simple. Like you do data augmentation at test time. You input the test sample. You do any random kind of augmentation, and then you derive different kind of data samples, and then you input this sample into the model. Oh, sorry, I should. And then you can compute the mean and the variance to compute the data uncertainty and model uncertainty. It's the same kind of pipeline, but the difference that it's doing Ensemble by applying the data augmentation or some applying data augmentation. The motivation is that the augmented test samples allow some exploration of different views, and then if the model can only handle one view and instead not another view. For example, let's recall the digit recognition task. If you rotate the one to like 90 degrees, and if the model cannot output the correct label, which means that it has high model uncertainty here. So this is motivation. It's usually used in medical imaging processing because in this area, the data augmentation is kind of common. It has some advantages like the post-hook, because you only do test time augmentation, you do not change the model, and it's post-time. You can it's model agnostic. No matter what model you use, you can also use kind of independent plug and play libraries to do this, and it's not require additional data. But it also has some problem. It's sensitive to different configurations, especially the augmentation. Like different augmentation you use will result different kind of uncertainties. It's kind of not robust, and it's also sensitive to the size of training data and the deep neural network architecture and the kind of this configuration. So it has been criticized for this part. And some of the people have proposed to do some progression in learnable test time augmentation, which means that you do not randomly choose data augmentation by yourself. Actually, you try to design a kind of a model to learn the suitable data augmentation. It's kind of like the active learning, or you just to find those data augmentations that can show more uncertainty. Yeah, but in terms of my memory, I think this part does not show very promising. And about the data augmentation, there are also some kind of questions whether the data augmentation can really reflect the underlying uncertainty.
In this case, do you compute the variance?
Yeah. You for input sample, you do different data augmentations, then you do different samples, or you compute different results and compute the variance to measure the model uncertainty. Because some simple augmentation like reflection is now able to capture much of the uncertainty, and some kind of special domain data augmentation like stretching or shearing captures more uncertainty. I think this kind of shearing or stretching is used in some other classification. I'm not quite sure. Just if you want to use this kind of test time data augmentation, it sounds simple, promising, but you have to be careful about the type of data augmentation you use.
You're allowed to crop the crop.
Yeah, you can crop the image, and yeah, you can
indicate the cat and dog, the crop maybe half the image, then you classify as dog.
Yeah. That's one of the way. For example, if you do crop, you in a large image, you only have a small part that's in distribution data, and do different cropping, maybe, yeah. Sorry, I skipped the most part about the calculation of uncertainty, and so here I only show some of them because it's most the max probability is like the confidence score. It's commonly used for capture the predictive uncertainty, which is the combination of data uncertainty and model uncertainty and the distribution uncertainty. It's kind of a whole concept. And then, yeah, and the people usually use entropy and variance to compute different entropy, different uncertainties in terms of different distribution they are modeling. I think if I and the mutual information is also widely used to model the model uncertainty because it measures the shared information between the labels and the models. I think the prior network one actually using the mutual information to compute the model uncertainty. Maybe if I have time, I can show you later. Yeah, and about the active learning, I just show some kind of application that how they will use data uncertainty instead of understanding the model. It's also do some other cases like the active learning. It's used uncertainty estimates to decide which data should be labeled. Because the biggest challenge in many applications is obtaining the labeled data. So the setting is that we, for example, we only have a budget like very small, 1,000 annotation that we can label. Then we should design a kind of acquisition function to ask what kind of label what kind of point we should label, which will make the final performance to be the best. And often it's based on the model uncertainty, which means that if this point has high model uncertainty, which means it might enter a point where the model is now quite the model is unseen because model uncertainty measures unknown of the models. Yeah, so it's a lot of active learning are using uncertainty as to identify the points, and this is one example about amnesia. And they use different kind of acquisition function, and the dropout. Let's just skip the details, and this random one is more like random, not capturing the real uncertainty, and this one is based on the Monte Carlo dropouts, and it has. Let's fix if we have only 400 labels that we can samples we can label. This is a budget. Then if you're using uncertainty estimates to identify the samples, you can achieve the lowest test error. So how to design a reliable uncertainty estimates to for the application of active learning is also important. Another one is reinforcement learning. It uses uncertainty estimates to decide when to exploit the environment. Because in reinforcement learning, there is some kind of exploit and exploration problem. And then we can use the uncertainty estimates to decide then at this time it can do some kind of exploration instead of choosing the strategy output by the policy with the highest reward estimate. And the original one is the ipsilon greedy search with just a sample digit. If it's larger than epsilon, then if it's larger than epsilon, we do exploration, or lower, we do we do exploit this kind of ipsum greedy search to avoid overfitting. And some kind of research that they use uncertainty estimate with Thompson sampling to do this exploit and exploration. It can have the faster convergence. So this is a kind of reinforcement learning problem. And if we use this uncertainty estimate based method to do the exploit or exploration, then it can has quicker convergence. For example, let's fix. We only conduct 100 batches, and it's already achieved higher reward than the baseline, the ipsum greedy strategy. Yeah. Yeah. And the last one is about the work of myself's work. It's kind of related to uncertainty estimation, but it's not that related to. It's more about the trustworthiness. So I just quickly share here about some kind of other line about uncertainty estimation, like you introduce different kind of inductive bias. Can I open? Thanks. This work is more about how it's more about the trustworthiness prediction. This task you can think about it's more like the misclassification prediction, which is to output a score. It kind of score similar to uncertainty estimate. If the model makes mistakes, then you output a low score. It output a high score if the model predicts correctly. This is the task, and it's just like this. When we applying this kind of medical imaging classification algorithms, we want to have a score to inform the doctor when the doctor can trust the classifier. Then we want to provide this kind of score the doctor can utilize to know when they should carefully look at this report, when they should just skip or quickly go through the result. And this one, this is a goal just to give kind of a score. For example, it's making the true prediction, then we give a high score. It's make a false prediction, we give a low score. This is kind of assumption goal. And the inductive bias we want to introduce is that we think we want to rely on the neighborhood homomorphy assumption, which means that the prediction of a sample is highly associated with the label of its neighbors. Let's look at this two-dimensional toy example. For this two-moon data set, if we use a linear class, if the original model is a linear classifier, then some kind of points are misclassified. Then if we can inspect its neighbors, then we can quickly find that most of the neighborhood in a training data set where we know the ground truth label. So it's all from orange, but some test points are classified as blue. Then there is some kind of disagreement. Then we know that they are highly likely to be misclassified. For this overconfident sample, which is classified by a deep neural network, it's highly the decision boundary is full of bells and curves, and it's prone to noise, like this kind of noise. And if we can inspect its neighbors, we can give a more reliable uncertainty estimate. And another assumption is that the classifier's prediction is also carries some information about the ground truth label. This method is post-hook method, so we only want to incorporate some kind of plug and play method to do this kind of thing. So we want to utilize the neighborhood information and also the classifier's input. Can you it's very similar because we are utilizing the neighbor homophily assumption, which nearest neighbors also share. But the difference is that we are not trying to only rely on the neighbor homophily assumption. We also want to introduce some kind of other information, and we also provide a kind of framework that you can introduce different kind of assumption into this. It's not just the classifier's output and neighborhood homophily, and here we only consider these two. And the framework is very simple, that we are only doing the class-wise neighborhood. Since here we only consider two kind of information that's very highly associated with the prediction. So we only compute the class-wise neighborhood feature and the base classifier's output feature, and we project them into the same space, and we do the aggregation to output kind of a score, and every class corresponds to every point. Yeah, distance. Yeah, you can choose its cosine similarity or Euclidean distance or some other distance. Yeah. And the experiment shows that actually our method outperforms other kind of post-hook uncertainties, post-hook one, like the confidence temperature score and some trust score and other methods that falls into the post-hook. And since we use the aggregation network, we try to understand how does this kind of aggregation works, and we find that you can just ignore these details. The high-level idea is that it's actually if we fix the projection space to be like this one and this one, the WH and WP, which is project the vector into the same space, and then if we fix them, it's actually equivalent to one-hop graph convolution neural network, which means that if we restrict to learnable parameters, then we are equivalent to one-hop graph neural network. This also says that our method is actually more flexible than one-hop graph neural network because it has more learnable parameters and can capture more information. This is some visualization about the WH and WP. This is the projection space weight matrix, and it's generally like the block diagonal structure. This is quite similar to the assumption of the theorem. But it also has some kind of difference, like in this, instead of setting every weight as a 1/k, we actually learn different kind of weights for different neighbors with different distance. So it's actually assign the highest weights to the most near samples and a little bit lower weights to the second near sample. This is reasonable, but this kind of intra-class relation is not considered in one-hop graph neural networks. So, yeah.
I guess the WH is the hop.
Yeah. WH distance to hop. Oh no.
No. I didn't get what you showed me. Because so maybe can you maybe repeat? So
Okay. Let's repeat.
I got the limitation.
Okay. I go back. That's where we obtain the kind of neighborhood feature, which is for every class we have compute its k nearest neighbors similarity, and also for this kind of classifier, we capture some kind of feature about its information, and then we try to project them into the same space, and the WH is a projection, and then we find that if it's fixed in this way, because for every class it has 1/k weights, and then it equals to 1 hop GCN. Yeah, and so the visualization shows similarity to 1 hop GCN, but actually it's not so. It's similar, but it's not totally similar because it's actually capture more information, which the 1 hop GCN cannot do. Yeah.
Thanks.
Yeah. And okay, let me. Yeah. And I just want to, okay, because actually, you may wonder why we only consider 1 hop GCN instead of multi-hop GCN. We actually do some experiments across several data sets, and we find that for this kind of misclassification prediction or trustworthiness prediction task, 1 hop graph neural net, 1 hop neighbors is already enough, because we already consider a little bit larger neighborhoods. So if the nearest neighbor is large, the neighborhood is already enough, then it's useless to consider the second hop neighbors. And we also apply this to another task associated with trustworthiness. It's a mislabel detection, which means that if the label, because we know that there are actually a lot of data sets we obtain, we are using now actually suffer from a lot of noise, like some misclassify, like during the training set, where this cat, but it's actually labeled as this dog, but actually labeled as cat, this kind of mislabels. And if we do not consider these labels and we're training this model, like we are decreasing the training loss to 0 or almost 0. Actually, we are overfitting to some kind of data sets. And in the I think it's in a paper in Europe's 2020 or 2021, it shows that even in CIFAR, MNIST, and CIFAR 10, CIFAR 100, and some other data sets, there are estimated error, label error of at least 3%. But actually, you are training to be 100% doing training. It's definitely overfitted. So one of the way to mitigate it is to do mislabel detection, to identify those mislabeled data. And the goal of motivation of this talk is this work is that if we classify a sample into dog with high confidence, is there any chances that maybe it's a one truth label that is not incorrect? So we try to design kind of reliability score utilizing the trustworthiness we already provide, and it's and this is the indicator function. If the y-hat if it's correctly classified, then this weight is 1. If it's misclassified, then this is minus 1, negative 1, which means that if the sample is misclassified with highest trustworthiness score, it should have the lowest reliability score in terms of a label. So by using this, we are actually identified some kind of mislabels. This is a core insensitive context. This is a context in the cargo, and we find that the data set they provide has a lot of mislabels. For example, they identify like kind of what's the past tense or past tense this question as insensitive, but it does not meet any kind of does not meet the standard they propose to identify the sample as insincere, because it does not, yeah. And also like this, what's the important thing, so steps when starting a film production company in Netherlands? This is definitely not an insincere question. So by using this algorithm, we actually can identify a lot of mislabeled samples. And we also provide some kind of negative, false negative guarantee, which means that if we for any given confidence alpha we want, then with probability at least 1 minus alpha over any random choice of any correctly labeled data, we have the reliability score larger than the threshold we choose, which means that if this is a correctly labeled samples, and if we choose alpha, or we choose a threshold based on this alpha in a certain way, the probability of this correctly labeled sample, their probability, they have at least a 1 minus alpha's probability. They won't be identified as mislabeled if they are correctly labeled. This is kind of false negative bound. Yeah. Yeah, that's kind of the end of this talk. Yeah. And the general takeaways, uncertainty estimation is critical for AI and machine learning algorithms deployment. So it's actually super important if you want to extend your model into real world applications. And there are 4 directions for proposing better uncertainty estimators. One way is single deterministic way, like the calibration, prior network, evidential network. The general way for doing this single deterministic way is to imposing the prior. some kind of inductive bias. For example, for the prior network and evidential network, while assuming their kind of categorical distribution is actually following a higher order distribution, which is Dirichlet distribution. And this is just for computational simplicity. It may not be correct. So if you can find a better kind of prior distribution, then it will be reliable. It will lead to more reliable uncertainty. And then there are also some other kind of research line, which is kind of non-Bayesian ensemble. For example, the diff ensemble we discussed, and it also has some kind of Bayesian-based neural network, like the Monte Carlo Dropouts. And also, you can do test time data augmentation. It's also ensemble-based. Oh, sorry. Yeah. And if you have any questions or any discussions, you can email me or just reach to me. And if you want to know more information and more literatures about uncertainty estimation, you can go through this awesome GitHub repo. It almost records papers from earlier to most recent papers. And there are also some recent surveys about uncertainty estimation. Yeah. I think that's the end of this. Yeah. Do you have any questions?
Can you share the slide? Yes.
Yeah, I can share. Yeah. But actually, I think there are more kind of tutorial that's much better than me. I can share you some link. Yeah.
But your slides are pretty good.
Thank you.
You need to.
Yeah, but actually, I think I adopted a lot of slides from the MIT one.
That's what we said about. You copy somebody's idea, then you improve it.
Yeah. Thank you.
So you with the previous method, did you try to apply to the image data sets that you said had 3% mislabeled?
For the mislabeled one.
Yeah.
We didn't extend this to image one, but we do have a follow work up, which is to do mislabel detection on graph data set. Because there is no recent mislabel detection research on graph data set. So we find it unflexible, and we do some kind of first we do some analysis, and we estimated that for several almost the most commonly used data sets in graph area, it's at least have 7 to 10% of mislabelings. And then we try to design some algorithm to detect these mislabels.
What's a graph data set?
It's more like the node classification data set, which like the PubMed, it's and some archive data set, kind of citation data set, like you predict which the node is following to which area is kind of graph data set. Yeah, but this is general to all the node classification data sets.
By misclassification, the graph data set, you mean that they misclassify?
Oh no. We didn't we haven't applied the misclassification algorithm to graph. We actually designed another mislabeled one. Because we currently this one is relies on the neighborhood. But on graph, the model itself already utilizes this kind of information. So what we are doing might be we'll only do minor contribution, and we try to gathering the all. Actually, we try to utilize this kind of neighborhood in a more in a strong way. Yeah. Yeah. Yeah, what we do in graph is more about mislabel detection. Do you have any question? So then thanks for joining this tutorial. Thank you.